All right, so this idea of using the chain rule to take the derivative of an inverse function allowed us to be able to take the derivative of ln of x. And so maybe it's worth trying in other places. We can try to take the derivative of arcsine. So if I have y is equal to arcsine of x, and I wanted to take the derivative of it, obviously I have no idea how to take the derivative directly, but I know the definition of arcsine. I know that this means that y is the arc, the angle, which has sine equal to x, meaning sine of y is equal to x. Now I can take the derivative of this. So take the derivative of both sides with respect to x, and that ability to simply take the derivative of a function of y, it's nothing major. It only gives us on the left-hand side cosine of y, but then times dy by dx. That's powerful stuff. That ability to have a function of y on that side, we take its derivative, what do we get? Just the derivative of that function times dy by dx. You always end up with that y prime sitting beautifully in the line of the equation, and all you need to do is take everything that's attached to it, divide by that so that it goes to the other side of the equation, and you've solved for the derivative. And the right-hand side, in this case, that's not very difficult at all. And so y prime is equal to 1 over cosine of y. I'd love to be able to leave it like this, but I can't. I want to be able to say what the derivative is with respect to x itself. So if sine of y is equal to x, what is cosine of y equal to? I've got a very nice equation that I absolutely ought to know. Sine squared y plus cos squared y is equal to 1. So sine is equal to x. That gives me x squared plus cos squared y is equal to 1. I'll skip a step over here. Cos is plus or minus the square root of 1 minus x squared. That's almost perfect. I need to figure out whether it is a plus or a minus. Well, that's actually straightforward. I go to the unit circle. If I take the arcsine function, what does it give me? It gives me only angles from minus pi by 2 to positive pi by 2. That's it. Those are the only possibilities. And what happens over those angles? Throughout, we're on the right-hand side of the unit circle, which means that our x-coordinate, our cosine, is greater than or equal to 0. And so what I need, what I can say, is that cosine of y is necessarily the positive square root, or the non-negative square root of 1 minus x squared. And so over here, y prime is equal to 1 over root 1 minus x squared. That is an awful 2. There we go. Still bad. But you can now go over the other arc functions. You can go to arc cosine, arc tangent, and the rest of them, and see what happens. The only one that I'm going to do over here, I'm going to do arc tangent, because it ends up being very nice and extremely useful for us when we hit integration. The rest of them I will leave and try to do those as exercises. So arc tangent, we approach in the exact same manner. Y is equal to arc tangent of x, therefore the tangent of y is equal to x. Take derivative of both sides with respect to x, and I get secant squared y times y prime is equal to 1. Y prime is equal to 1 over secant squared, but secant is 1 over cos, so I have 1 over cos squared, and so this is equal to cos squared of y. And now I need to figure out exactly what's what. I know that, which direction shall I go at it? Probably the one that says that 1 plus tan squared of theta, in this case of y, is equal to secant squared of y. And so 1 plus x squared is equal to secant squared. I don't even need to worry about pluses and minuses. I don't need to start drawing right-angled triangles and using SOHCAHTOA in order to figure out what's what. I have my identity, I plug stuff into it, and everything falls through from it. So I didn't even need to clean this up into cos squared. 1 over secant squared is perfect. This is equal to 1 over 1 plus x squared. And there are plenty of reasons to write it as 1 plus x squared instead of x squared plus 1, so I recommend it. It's not just that it works better from the identity as we learned it, as we derived it, but it also works very nicely for some of the things that we will do in Chapter 5 in integration, or in Chapter 6.